Okay. Hi. This is the first lecture of the new online instruction, remote learning, whatever you want to call it, part of the course. We're going to be doing this for a while now, possibly the rest of the semester. For right now, it's going to be kind of low tech because I'm still figuring out the technology thing. So there's not going to be much editing or flashiness on videos. It's just going to be kind of simulating the oceanography, ocean circulation, both on the surface, which is what we'll be talking about today, waves. There's many different types of waves and how they move. Chapter 9 is about the tides, how the water moves with due to tidal forces, and then chapter 10 is about shoreline processes. How does all this moving water with the currents, the waves, the tides, how does that affect the coastal regions of our oceans? So this is physical oceanography, and the name kind of it's a big hint there is what the name means. It's the physics. So there's going to be a little bit of math involved, but we're going to get through it together. Don't sweat it too much. So follow along, take notes just like you would in class. And during my virtual office hours or on the Canvas discussion boards, that's the place to ask me, ask your fellow classmates any questions you have. I prefer to do it on the discussion board because other students guaranteed will have the exact same question that you do. So if you can post it there and I can answer your question for you, I will end up answering the same question for probably a dozen or 2 dozen other students all at the same time. So that would be the best way to do it. So let's just get into it. Like I said, I'm going to try to figure out the technology on the fly. There's a big old whiteboard behind me, just like there would be in the lecture hall. And most videos won't have it, but today, this lecture is whiteboard intensive. So you'll see me drawing on this guy, a beautiful piece of artwork over my shoulder as we go. So if you have colored pencils along and draw along, that's what I would totally recommend you do. If you're at home, pause this video, grab some colored pencils. I'm going to use red, blue, and black. So if you want to get the same colors, you can have a drawing on your sheet of paper that looks just like the drawing on my whiteboard by the end. Yeah, so let's just get into it. Ocean circulation. Let's get started. Ocean surface currents are driven by the wind. So it's a real great thing that all of us are now experts on how the wind and weather and atmospheric circulation works. We just studied that and took a test on it from the unit. So some of that's going to come into play today. Actually, a lot of it's going to come into play today. Deep ocean currents, that's more due to the density differences and different types of water in the deep ocean. We'll get to that at a later lecture. It's very straightforward, actually. So we actually don't need to spend too much time there. The reason the water is moving at all in our oceans through these currents is the same reason that the air was moving. The air was doing about 2/3, as you can see here. Let me see if I can get the little laser pointer thing. There we go, laser pointer. The atmosphere, the air currents, the Hadley, the Ferrel, the polar, all that circulation that we were talking about in the last unit of the course, that does about 2/3 of the work as far as distributing the heat from the tropics, from the equator to the poles, the north and to the south. The oceans, as you see here, they're going to end up doing about 1/3 of the, but So what we're going to talk about today is the surface ocean circuit. The rest of the ocean is not affected hardly at all by what the wind is doing up top. So while we're going to be spending this lecture talking only about temperature, talking about just what's going on down below, the other 90% of the ocean water. As I mentioned earlier, it's very straightforward. It'll take us maybe 5-10 minutes tops to get through it. So surface ocean. It is the water to move. But we saw in the last section when we talked about I believe low density material pushing on the water, which is such a high density material, at least relative to the air, the water's going to be kind of stubborn. It's not going to move as fast as the wind. So that's where we lose about 98% of the wind's energy as far as what gets transferred into the ocean currents below. But that 2% is enough to get the water moving. And as we'll see today, we're going to learn exactly how it moves. The other thing that is going to be a carryover from the last section, the wind belts we talked about. It's on the next slide here. We talked about the trade winds here, the northeast trades and the southeast trades. Remember, we named them winds for where they blow from, not where they blow to. And we also have the westerlies up down here and way up here. Blow between about 30 degrees to about 0 degrees in the north and southern hemisphere. And the westerlies, they are the surface winds of the Ferrel cells, which run from about 30 to 60 degrees south of the equator and 30 to 60 degrees north of the equator. What we're looking at on this side, what I want you to note is that we're only looking at the orange arrows. I do not care about the blue arrows, just the orange arrows. I'm going to go over here to the side here, just the surface winds of the Hadley cell. So the Hadley cell, all these atmospheric circulation cells, they have these big loops, right? But when the air is up here, we don't care what the air is doing far from Earth. It's down here where it blows across the Earth's surface. That's where the transfer of energy is going to take place. So it's just the orange arrows, just the bottoms of these convection cells, just the surface winds of the Hadley, known as the northeast trades, the surface winds of the southern Hadley cell, known as the southeast trade, and then the surface winds of the Ferrel cells, known as the westerlies, in both the south and the southern and northern hemispheres. On this diagram, you'll see that the trade winds are now shown in purple, and the prevailing westerlies, as they're called, are shown in green. And as we said, that wind friction is one of the forces, one of 3 forces that are going to cause the surface ocean currents to move. Now, there are 3 forces, and the tricky thing about this, the reason this is going to take us pretty much the whole lecture today, is that all 3 forces are playing a role at the same time. It's not like this guy's going and the other 2 are turned off for a bit. They're all going at the same time. So it's going to be kind of a dynamic situation as to how exactly these winds, the trade winds or the westerlies, how they make the water move beneath them. The other 2 forces, as you can see here, the Coriolis effect. There's our friend Gustav Coriolis coming back to haunt us once again. You thought he was done after the last exam. Nope, he's back. Because again, all of this movement of ocean water, just like it was for the moving air, all of this movement is taking place on a rotating Earth. So the good news is, the bad news is that we still need to discuss the Coriolis effect. But the good news, you're all experts on the Coriolis effect. You learned all about it already. So we're just going to put the knowledge that we already have to use here, and we're going to understand how it works for surface ocean currents. And then the last force here is pressure, which I will just refer to as gravity. Okay, so wind friction, Coriolis effect, and this thing called the pressure gradient effect. As I just said, I'm just going to refer to as gravity, because gravity, as we know, things get pulled downhill due to gravity. That's pretty straightforward. And what we get with the combination of these forces is what's called a geostrophic gyre. I'll go back one slide. You can follow along here. On the previous slide, we see underneath the purple arrows and the green arrows, we see this blue loop with these 4 arrows all looping around together. And there's another loop down here in the southern hemisphere. That is the geostrophic gyre. Okay. The gyre is a large circular loop of moving water. And as you on that diagram, 2 slides ago now, 1, 2, 3, 4. 4 arrows make the geostrophic gyre in the northern Atlantic Ocean, and another 4, a set of 4 arrows makes the geostrophic gyre in the southern Atlantic Ocean. Every gyre has the same 4 currents in it, or the 4, I should say, types of currents in it. The types of currents are, there's going to be an equatorial current, there's going to be a western boundary current, there's going to be an eastern boundary current, and then depending on which hemisphere you're in, either a northern boundary current in the northern hemisphere or a southern boundary current if the gyre is a southern hemisphere gyre. And they're called subtropical gyres because in the middle of the gyre, if you go back a couple slides here, right there, in the middle of the gyre, right where the red dot is there in the north and the red dot is here in the south, that's about 30 degrees away from the equator, which is technically called the subtropics. You're just outside of the tropics. You're south of the Tropic of Capricorn here, and you are north of the Tropic of Cancer in the northern hemisphere's gyres. So here's your whole world map of all the ocean currents labeled. So I want to show you first the equatorial currents. They are either just north or just south of the equator, as you can see here. Hopefully you guys can see this little red dot I'm using to point out, just like I would with my laser pointer in the lecture hall. There's an equatorial current here in the Atlantic and a south equatorial current in the Atlantic. There's an equatorial current in the Pacific and an equatorial current in the Pacific. The Indian Ocean has the same 2 currents also. It has kind of the same name no matter which ocean you're in. So it's kind of nice. You'll notice that all of these equatorial currents are colored red, and you'll notice that they are flowing from the east to the west. So they travel westward along the equator. They all have that in common. The reason they're red, as you've probably already guessed by now, is because they're warmer currents. Why are they warm? Because they're right next to the equator. Everything's warm near the equator all year round. Okay, those are equatorial currents. Next, we're going to talk about the western boundary currents. The western boundary currents. Now, here's a critical thing to understand. This is an oceanography class. We have to think ocean first. Don't look at a map and look for the green patches of land. Look at the world map and stare at the blue parts first. Now, when I say a western boundary current, you have to look to the western side of the ocean basin. We live in California. We are on the west coast of the United States. But the water there off the beach of whatever the beach is, Huntington or Newport or Laguna or whatever, Long Beach, that's not the western side of the Pacific Ocean. That's the eastern side of the Pacific Ocean. The western boundary current is going to be on the other side of the Pacific Ocean, way over here off the coast of the Philippines and Japan. That's called the Kuroshio current. The western boundary current in the North Atlantic is called the Gulf Stream. That's the current that runs along the United States East Coast. But remember, it's on the western side of the Atlantic Ocean. Western boundary currents on the western boundary of the Atlantic. You also have the Brazil current down here to the south in the Southern Atlantic Ocean off the coast of Brazil, cleverly enough. There's the Agulhas current. And those Finding Nemo fans here are probably familiar with this current. It's called the AC, known for, which stands for the East Australian current. It's, if you've seen Finding Nemo, it's the really fast, warm waters that Nemo and I can never remember the guy's name, the sea turtle, the surfer dude, sea turtle, whatever. Just watch Finding Nemo. It's a good movie. Okay, that's the EAC. They're all western boundary currents. What color are they? They're all red. It's warm water. Okay, and you can all see that these arrows, Kuroshio, East Australian, Brazil, Gulf Stream, and Agulhas, those arrows are moving away from the equator. In the northern hemisphere, they are moving to the north, and the ones in the southern hemisphere are heading southward. But what they all have in common is, no matter which hemisphere we're in, they're moving away from the equator. And they're red because they're warm. Now, here's the thing about the temperature of these currents. The temperature of the current is determined by the water that flows into that current. In other words, the question you want to ask yourself when I ask you about the temperature of a current, and I guarantee you I'm going to ask you about the temperature of the currents, take the hint, is where did this water come from? The Gulf Stream is warm. Why is it warm? Well, where did it come from? Oh, it came from the tropics. It came from near the equator. I would expect that water to be warm. And because water has a high heat capacity, it's not going to cool off all that fast. We learned that already about the water having a high heat capacity. It's slow to warm up, and once it gets warm near the equator, it's going to stay warm even when it starts to flow away from the equator in these western boundary currents. And now we're also going to have these, the next current are these northern or southern boundary currents. Again, this depends on which hemisphere you're in. The northern gyres will have a northern boundary current. Here it's called the North Pacific Current. And the Atlantic over here, it's called the North Atlantic Current, cleverly named. I'm sure you agree with me there. Now the southern boundary currents are a little bit tricky, and we'll get to them later on in the semester. They don't have, it looks messier down here, and it is messier down here. So we're going to skip that for now. I promise you we'll get back to it. And then lastly, we have the eastern boundary currents. All of these gyres have these eastern boundary currents. In the North Pacific, it's called the California Current. That's the current that's off the coast here of California. The North Atlantic has what's called the Canary Current. It flows right where I'm going to put the red dot right on top of them. There's a little chain of islands right there. They're called the Canary Islands. The current flows right through them, so that's where it gets the name. There's the Peru Current here in the Southern Pacific Gyre off the coast of Peru. And then you have the Benguela Current. I don't know what that name means. It doesn't matter. And then also you have, it's kind of cut off here on the image, but there's the West Australia Current. I know it's tricky. It's the West Australia Current, even though it's an eastern boundary current. Again, eastern boundary because we are on the eastern side, in this case, of the Indian Ocean, but they named it for the west coast of Australia, which is confusing. There are equatorial countercurrents. It's just a little bit of water right here that sneaks its way through, right between those northern and southern boundary currents. They're moving this way. I have to do this backwards. They're moving this way, and there's a little bit of water that's fighting its way through traffic. These equatorial countercurrents, especially here in the Pacific, it's something we're going to talk about in the next lecture. So I'm pointing it out to you now so that the next time I can just be like, remember that thing we talked about? This is that thing we're talking about. They'll have them. There's an equatorial countercurrent in each ocean. And we also have these little things called subpolar gyres. There's one way up north here it's almost in the Arctic Ocean. There's one here off the southern coast of Alaska. And there's a couple down here off the coast of Antarctica. Again, I'm only pointing these out to you now. We're not going to talk about them hardly at all in this lecture, but in the next lecture, they're going to play an important role. So hang on to that for a moment. Even if you didn't have the full map showing you where all these currents are moving, if all you had to go on was water temperature, you could still see the circulation of the water. You could, without this white air drawn here, the fact that this green, cooler water is kind of looping and curling its way up along the coast here, that tells me that the movement in the water is kind of dragging it there. And you can see here, this warm water here in the North Pacific, it's getting pulled northward away from the equator due to the current over here moving it away from the equator. So if all you had to go on was just the water temperature kind of show you how this, circular looping pattern of water in both the northern and southern hemispheres works. Now, let's get down to the details here. This is called the Ekman spiral. Oops, I lost my PowerPoint. The icebergs wouldn't go the same direction as the wind. They would to the side. Why to the right? Because of the Coriolis effect, because this observation was being made in the at first and they were seeing the icebergs and the boats and everything. So the Coriolis effect creates something in these surface waters called the Ekman spiral. Now, the Ekman spiral is the physics of the Ekman spiral start with the big green arrow there, right here, the wind. When the wind blows across the ocean, the water beneath it, as we talked about earlier, about 2% of the wind's energy goes into the water, and the water wants to go where the wind is pushing it, but it doesn't go the same direction. Coriolis says you can go, you can move, you have to move, but you should move slightly off to the right. And so you'll notice here, relative to the wind direction, the surface current, this dark blue arrow here, it is moving off to the right at an angle that's different than the direction that the wind is blowing. So why do we call it a spiral? Because we're going to go down deeper beneath that surface water, down here to where the pink arrow is, 10, 15, 20 meters deep. And that second layer of water, the second layer down here, it's getting affected not by the wind, it's getting affected by the surface water. So the water is only going to get pushed around by whatever's just above it. The surface water gets pushed by the wind because that's what's above it. The second layer, the pink arrow there, is getting pushed by the blue arrow. And so it moves slightly. Hopefully you can see this on the diagram. The pink arrow is turned slightly to the right of the blue arrow. Coriolis is shifting it to the right. And then this gray colored arrow in the third level, it's slightly to the right of the pink arrow, and so on and so forth all the way down. And these arrows keep turning to the right because the Coriolis shift, as each step we go down deeper and deeper, pulls things to the right. You'll also notice that the arrows are getting smaller. That's a way of drawing something that shows you relative speed. It's called a vector. If you were in a math class, it's called a vector. When you draw a long arrow, it's indicating fast moving water. When you draw the arrow shorter and shorter and shorter, as you see here moving down the spiral, it's showing you that the water is getting slower. The reason the water gets slower is because of friction. All these water molecules with those hydrogen bonds, strong handshakes, there's just going to be friction like there is in any scenario with physics. Why does a person on a skateboard have to keep, kicking to keep moving on the skateboards? Because friction's slowing them down every step of the way, or every roll of the way, I guess. So friction is slowing it down, and it slows it down so much so that when you see here at the bottom of the spiral, two interesting things are happening. The first interesting thing is that the orange arrow is 180 degrees, completely opposite what the wind up at the surface is doing. So that's kind of interesting, that if you get deep enough into the water will be moving backwards relative to what the wind up at the surface is doing. But the wind is what's causing all of the movement to take place. The next thing is, what's below the orange arrow? There are no more arrows. When there's frictional loss every step of the way, at some point you're going to lose everything as far as your speed goes. Your speed drops by 10%, and then it drops by another 10%, and then it drops by another 10%. At some point you're going to hit zero. At some point beneath this Ekman spiral, you will get deep enough to where the water is perfectly calm, whereas the water just above it is moving slightly, the water above that is moving faster, and the water up at the surface may be moving very fast because there could be some high winds or storms or something going on up at the surface. Okay, so this Ekman spiral is tricky. There's a bunch of arrows on your screen right now, but let's simplify it. Look at that big brown arrow off to the right. Excuse me. That big brown arrow is how we simplify this whole thing. Let's treat this whole 100 meters, the whole top, not just, just the blue arrow, just the pink arrow, but all of this water that's moving, let's lump it together and average it out. Average it out as far as its speed and average it out as far as its direction goes. And we're going to learn that if we do that, we learned that Ekman transport moves the water 90 degrees to the right of the wind direction in the northern hemisphere. and 90 degrees to the left of the wind direction in the southern hemisphere, because hopefully you'll remember, and if not, here's your reminder, that this whole thing starts because of the wind, and these directions that we're turning are because of the Coriolis effect. Everything we are talking about so far, and probably all day today, is happening on a rotating Earth. So Coriolis effect kicks in here. And so Ekman transport says the surface winds want to move 90 degrees to the right of the wind direction in the northern hemisphere. I'm going to focus on the northern hemisphere because that's where we live, and the diagram behind me is a picture of the North Atlantic Ocean. That's what I'm going to be drawing for you today. So let's get to that drawing. Let me close this. Come on. You'll hear me click things. I'm going to give me a second to figure this out. Okay. Hopefully, okay, I should be in full screen mode here now. So I want to point out a couple things. The wind is what's causing this, the surface ocean to move. So let's go back a couple slides and remember, wind are we talking about? This is a green marker. I don't think it's going to show up too well in here, but I'm going to make them grow nice and huge so that it's pretty clear. So down here, so actually, let me start down here. Down here, that's on the screen. Yeah, that's the equator. Okay, there's your equator. So just north of the equator, those winds were called the trade winds, and they move. I just erased some of my dots here. Yeah, right here. The trade winds, big old green arrow. Just want to see if that, yeah, it's showing up. Okay, good. We can see this. Trade winds. You can't read that, but that says trade winds. And up here, we have the westerlies. Fill this in so they show up. There we go. Westerlies. Nope, either. A little bit better. Okay. Those are the winds that are getting things started here. Now, Ekman transport says that in the northern hemisphere, if the wind is blowing across the water here, Ekman transport says, well, that means the water wants to take a 90-degree turn. That's a 90-degree right angle, corner right there. That's a 90-degree angle. That is Ekman. Ekman transport. And there's one here. That's Ekman transport. I'll just put ET next to it. ET. Got it. Okay. So far, so good. We got our winds. We have Ekman transport, but there was a third. Are we seeing this now? Okay. There was a third force at play here. The third force at play is gravity. So what we start to see happening with these geostrophic gyres is we get what's called subtropical convergence. We get in the middle, and I'll go back full screen in just a second. We get a mound of water here, a big hill of water in the, can you see that? Sorry, I'm just figuring this stuff out. We get a hill of water mounding up here in the middle of the gyre. Why? Because Ekman transport from down here is pushing it towards the middle of the gyre, and transport from the north is pulling that down towards the middle of the gyre. And so if I had on my table here, if I had a bunch of dry sand and I pushed the dry sand from one side and from the other, you're going to get a bunch of sand piling up in between there. So when the forces are these kind of inward pushing forces, like the Ekman transport forces are, you get a hill of water there. Now, because we have a hill of water, this is where that third force kicks in, pressure gradient, AKA gravity. Gravity, as you can see here, right here, gravity, it pulls things down off the top of the hill. That's just how it works. And so the water wants to flow downhill. So skip ahead a couple slides. Actually, no, I'm just going to go back to the whiteboard. We'll finish on the whiteboard. And we'll do this. And okay, let me fix this. There we go. So what do we have going on here? I'm just going to erase some of these dots. We have force number 1, wind friction. Force number 2, Ekman transport. And then we're going to have force number 3 that says, because there's a hill of water here and gravity pulls things downhill away from the hill, there's a third force that's going to happen right here. And that is pressure gradient, another force over here, away from, right? These red arrows are going away from the hill. I'm just going to call it gravity over here because that's really all it is. Okay, it's gravity. If you've ever shook everything, if you've ever seen an hourglass, sand falling out an hourglass, it will land in the hourglass and it will pile up. And so the sand will pile up in the bottom of the hourglass, but as the hill gets taller and taller and taller, gravity will kick in at the middle of the ocean. And we just know that's not true. We have these 3 forces: wind friction, Ekman transport, pressure gradient, AKA gravity, all acting on the sand here further north in the Atlantic Ocean. So what we're left with the current here, the wall is heading over to here. This is the end of our loop. And so the current here in the North Atlantic Ocean, right through those 2 points, and the water down here more or less flows from here over to here. Pretty much flows straight across there. I did a horrible job drawing that bottom arrow. But what you're going to see here is that relative to the wind direction, the ocean current will actually move 45 degrees to the right of the wind direction. The wind was going here, and there's a 45-degree angle, and the current is going there. The wind is going here. Our trade winds are heading down that way, and the current is, again, 45 degrees to the right. That's a very poor arrow, but whatever, you get the idea. And we have two of the, currents in the Atlantic fire. So now something else is going on here. And we've already talked about it, but something else is going on here. And what's going on is that the Earth is rotating. So again, I'm going to go back to this analogy of a of having like a pile of sand. If I had this pile of sand on one of those like plastic cafeteria trays, and I took the tray and I shifted it quickly off to one side, I think we all get the idea of that sand in the middle of a plastic tray. It wouldn't stay in the middle of the tray if I rapidly shifted the tray off to one side. It's because we sat in a car that came to an abrupt stop, or we sat in the ocean, but because the whole earth is spinning, it kind of sloshes and stop. You kind of lurch forward. This lurches off the side. The car taking a quick turn. Everybody in the car, when the car takes a hard right, everybody shifts, whoa, way off to one side. And that's kind of what happens here. Due to the rotation of the earth, sorry to those of you who did this in pen, that pile of water, it actually shows up over here off to one side of the ocean. Toward the western side of the ocean, over here. Which reminds me, I didn't even name these currents. Actually, I named them before. This is the North Atlantic Current, North ATL. This is the North EQ Equatorial Current down here. And this current over here is also has its own name. It's called the Gulf Stream. That's the Gulf Stream current over there. I'll zoom back in so you can actually see that what I just wrote. The Gulf Stream current off the east coast of the United States is, due to western intensification, it is the fastest current in the North Atlantic Gyre. How fast is it? It's Olympic swimmer speeds fast. It is probably twice as fast as any one of you can swim, unless you guys are Olympians. It's your Michael Phelps, it's your Katie Ledecky, name your fast Olympic swimmer. It's fast because it's getting squeezed. I'll go back so we can see the whole picture now. It's getting squeezed between the east coast of the United States. This is very difficult to do. I don't know how a weather person does this. It's getting, the water's getting squeezed between the east coast of the United States and this pile of water here. So it's like when you have a garden hose and you kind of put your thumb a little bit over the end of the hose, what happens to the water that's coming out of the hose is it speeds up. You give it a narrower opening to get through, the water's going to go faster. This hill of water gave the Gulf Stream a narrower pathway to get through, and so it speeds up through there. It's going twice as fast as you can swim. So if you get shipwrecked off the East Coast, not be worth it to try to swim back to your boat because the current may end up carrying you faster than you can swim. But on the other side of the ocean, the opposite thing is true. This current is called I can't even write it on here, the Canary Current. It moves, you can probably outswim it. It's a very slow current. It's the slowest of these four currents in the North Atlantic Gyre. The North Atlantic Current and the North Equatorial Current are like your average medium speed. They are the speeds that an average swimmer can move. So the Gulf Stream gets intensified by the narrow pathway that it has to move through. So it's narrow, it's fast, it's deep. I don't really care about the depth of these currents, and we already talked about why it's warmer. Remember, describe a current's temperature based on where it's coming from. The North Equatorial Current is feeding into the Gulf Stream. The North Equatorial Current is going to be plenty warm because it spent weeks down there near the equator, maybe months. Oops. Eastern boundary currents, as we just talked about, like the Canary Current, they're the opposite of western boundary currents in every way. They are cold water, not warm water. They're slow currents, not fast. They're shallow, not deep, and they're wide, not narrow. because they're wide, because you have a wide path to get through, the water is able to move a lot slower through there. Narrow paths like your thumb over the garden, the water's going to go fast through there. That's not the case with the Canary Current. And here's the other thing. It's not the case with the Canary Current, as I just said. But what I just described about the Canary Current goes for every eastern boundary current. It goes for the Benguela Current. It goes for the Peru Current. And it goes for the current right off of our coastline here in California, known as the California Current, because that is another eastern boundary current. All eastern boundary currents are cold water, slow relative to the other currents in the gyre. They're wide. And they are, as you can see on the diagram behind me, they flow towards the equator. So there's 4 names of the currents on the board behind me. I just about the California Current also. Those are 5 currents that I want you to know. I want you to know a total of 6. We'll get to the 6th one a little bit later. I want you to know, of all the ocean currents in the surface ocean waters around the world, there's only 6 currents that I want you to know. 4 of them are right here: the Gulf Stream, the North Atlantic, the Canary, and the North Equatorial. The 5th one is the water you may have been swimming in the last time you went to the beach, whenever that was. That was the California Current. And then the 6th one we'll get to later. I want you to be able to name those 6 currents. I want you to be able to tell me which ones are the fast ones, which ones are the slow ones, which ones are the normal speed, which ones are hot, which ones are cold, which ones flow towards the equator or away from the equator, or do they flow eastern, or do they have an eastward or a westward direction? So direction, speed, temperature, width, name, right? So yeah, width, depth, speed. I don't care about depth. Temperature. So a western boundary current, as we just showed you, the Gulf Stream, I'll put my little dot right there. The Gulf Stream is the classic example of a western boundary current. If you can describe the Gulf Stream current, you can describe any western boundary current, as you can see there on the screen, like the Brazil Current or the Kuroshio Current. If you can describe the Canary Current, what's it like? Temperature, speed, width, etc. All eastern boundary currents are going to be like that. So this little table here is for the readers out there, and we have the pictures for more of the visual learners amongst us. So there's a strong impact that we here in California feel due to the currents off of our coast. And it's not just here in California, it's any coastal region. If the current off the coast is a warm current, like behind me, like the Gulf Stream here off the coast of Florida, the climate in that coastal region is going to be warm and humid. And this is something we talked about before. Why does the climate get warm or humid? Well, the heat from the water up the air. The warm water tends to give off evaporation and water vapor to the air. Your heat and humidity, as we talked about with the fuel of a hurricane and stuff from the previous section, the air masses are directly and immediately and dramatically impacted by these ocean currents. So a warm ocean current near the coast is going to create a climate of that coastal region. Anyone who lives near the shore is going to feel more warm, hot, and humid days than other types. If there's a cool current near the coast, like there is here off the coast of California, it's not that we don't have hot days, but the hot days aren't as hot as they could be because that cool water right off of our coast is able to absorb that much more heat for us. That cool water right off of California's coast doesn't have such high rates of evaporation. So we don't get that really nasty, sticky, muggy, excessive amounts of humidity in our climate. We have a very dry climate, and the temperature swings in our annual temperature swings throughout the year are pretty mild. Summer's warmer, winter's cooler, but it's nothing like it is in other parts of the world. Okay, let's keep moving. Skip it, I don't care. The next topic is upwelling and downwelling. So within these surface waters, there is a little bit of vertical motion up and down. When we get deeper water to come up to the surface, that's going to be called upwelling. When we get surface water to drop down, that's called downwelling. But how is the water beneath the surface different than the water up there at the surface? We've talked about this before. Warm water floats on top of cooler waters. So when you get that deeper water to come up to the surface, it's bringing that cooler temperature up to the surface. And the other thing that the deeper water will have is nutrients, because every time, is gross, every time a fish poops, that poop sinks. Every time something dies and sinks, that dead organism could be a bacteria, an algae, something tiny, or it could be an entire whale or something, or anything in between. Dead stuff sinks. Digested material, to put it delicately, sinks. And as that stuff sinks, and certainly as it sits there on the seafloor, it decomposes, it disintegrates, it deteriorates. And when it breaks down, I mean, all the way breaks down, it will become nutrients, nitrogen and phosphorus and magnesium and calcium and all this stuff enters the water. And so these deeper, cooler waters are often very nutrient rich. And this is why upwelling and downwelling is such a critical topic, is that when upwelling happens, it doesn't just bring cooler water up to the surface, it brings cool, nutrient rich water up to the surface. And the things that live up at the surface love that nutrient delivery when there is upwelling, because it boosts the whole food chain. And anybody who's gone fishing can appreciate that, because when there's upwelling and the nutrients are coming up to the surface, the tiny critters that feed off of those nutrients, they're going to show up. And then the small fish that feed off of those tiny critters, they're going to show up. And then the big fish that feed off the small fish, they're going to show up. And the whole food chain, and then the fish that you're out there with your rod and reel trying to catch, they may show up. You're going to have a better time fishing when there are upwelling conditions in the water. When there's downwelling, it's taking the surface water and pushing it further away. And so that deeper, cooler, nutrient-rich water, it gets pushed even further from the surface. Going fishing on a day when downwelling is taking place is not going to be as successful as fishing where upwelling is taking place. So downwelling takes place in the center of the gyre. So I'm going to go back to my screen here. I think you can see this. Remember these two blue arrows here pushing the water to the center of the gyre? When that surface water gets to the center of the gyre, like something's got to give. We talked about this when we were talking about atmospheric processes. We talked about how, let me get my little pointer back here. We talked about how when the winds aloft converge, I gave the analogy in class of you're driving on the freeway and there's a car coming on the on-ramp next to you and you got a car, you have to get out of there. These cars are merging close to one another, and whatever was between them, could be you got to either speed up and get out of there or slow down and let them merge in front of you. When these winds converge, the air that was between them gets squished and displaced downward, gets pushed out of the way. The same thing happens in the surface waters. As the surface waters converge, thank you, Ekman Transport, converge together, the water that was between there, it gets forced downward out of the way, and that triggers downwelling. So if you want to go deep sea fishing, this is not the spot to go. This is a bad spot to go. There's going to be downwelling, which means there won't be nutrients at the surface. And if there's not nutrients at the surface, there's not going to be a vibrant, healthy, thriving ecosystem of things that you may want to catch on your fishing pole or net or whatever you're using. I don't know. Low biological productivity is what this slide says. It means fishing. Now, you want to go deep sea fishing. Might I interest you in going near the equator? Not only is the weather going to be better, but remember our friends, the trade winds, which I'll show on this diagram with orange arrows. The trade winds are converging towards the equator, and you may be thinking, like, you were just talking about converging waters, but remember, Ekman Transport says the water's not going to go the same way that the wind. Ekman Transport says the water near the equator is actually going to move away from the equator. That's diverging. The waters there are diverging, which, as we talked about with the atmosphere, When it diverges, it creates this gap in between as they spread apart, and the deep water is going to come up to fill that void. And so you get nutrient rich water near the equator. That's where, like, deep sea fishing in the tropics, there you go. That's if you want to actually go out and catch some fish, that's the place to go. If you want to just, spend a few days on a boat, drinking margaritas or whatever, then go to the subtropical gyre. You won't catch a damn thing. You also get coastal upwelling. This is like if you go fishing here off like the piers at Huntington or whatever beach, this is what you're going to want to pay attention to. And this is what the coastal fishermen and women are paying very close attention to. People who work in the commercial fishing industry are kind of like amateur oceanographers, amateur meteorologists. They're not amateur, they're like professional oceanographers and meteorologists. They are tracking the wind very closely, because they know on this diagram here, if the wind off the coast of California, let's say this is California, if the wind off the coast of California is coming down from the north, that means Ekman Transport says it's going to take a right turn. Follow the little arrow, the little red dot there. Ekman Transport says you're going to take a right turn, which means the surface waters from the coast are going to get pushed away from the shore. When the surface waters get pushed away from the shore, the deeper waters from below come up to fill that void. You can see that happening with this little black arrow down here. The deeper waters come up from below to fill this coastal region as the surface waters get pushed away from the coast. That brings, as we said, that brings nutrients up to the surface. And so when the winds are coming from the north along California's coast, if you are the owner of a fleet of fishing boats, you're going to send everybody out on that day or those days, because fishing's going to be good. You're going to want to, pay those early wages and pay for all the gas on the boats or whatever. Spend all that money, because you're probably going to catch a whole bunch of fish during this period of upwelling. When the winds shift, and now they come, as you can see on this new diagram, from the south, that Ekman Transport pushes the water towards the coast. And when it gets there, it has nowhere else to go but down. Follow the little red dot here. It goes down. That triggers downwelling. So southerly winds along California's coast tells those in the fishing industry, maybe let's hang back a little bit. Maybe send a couple boats out, catch a little bit of fish, but let's not, invest too heavily in this. Let's just wait for the wind to shift and come back from the north, and then we'll get out there and the fishing will be good. We got to let the upwelling happen to bring the nutrients. When the nutrients are there, the whole food chain, including the fish that we want to catch, are more likely to be there. That's a better investment. This little diagram here, it shows you, we talked about like off the coast of Hawaii. This diagram here in the bottom left corner of the three images shows you how and why off of one coast, one side of some island, it may be better fishing because there's, I'm off the camera here, upwelling is taking place off of one side of the island, because as the current hits this island or table mount or seamount or whatever the feature is, it has nowhere to go but up, bringing with it the nutrients to the surface. So the fishing over here is going to be great. The fishing over here is going to be whatever. The last thing here, this last bullet point is really critical. Pycnocline. There's that word again. Pycnocline. We talked about I forget it was on the exam. The halocline, I think, was on the exam when you're measuring salinity. The thermocline is when you're measuring temperature. The pycnocline is what we call it when you're measuring density. So I'm going to go back a million slides real quick. Hang with me here. Let's go back a million slides. Boom, right there, right here. When there is no pycnocline, in other words, when we're in the high latitudes, so we're off the coast of, say, like the Arctic Ocean or the Antarctic Ocean, those waters are ridiculously cold. They're so cold up at the surface that they're just as cold down below. So there is no density contrast. Without a temperature contrast, there's no density contrast. And with no density contrast, those two layers of water can mix freely, and they do mix freely. And so in really cold surface areas, The deep water can come right on up to the surface, bringing with it the nutrients. Whereas in warmer waters, lower latitudes, you see here, there's a very strong density contrast from the surface to the deep. And just like how those of you who know like Italian salad dressing with oil and water, it doesn't mix all that well. You got to shake it up before you pour it on your salad or whatever. Warm water and cold water have a very strong density contrast. When there's a strong density contrast, the deeper water can't get up to the surface. It's too heavy. The surface water's too light and it can't bring the nutrients. But when there's no pycnocline, because everything's cold and everything's dense, come on up, nutrients. The fishing's going to be great. Let's go back to where we were. We're getting there. Just a few more minutes. Maybe. Okay. I mentioned earlier there are 5 currents I want you to know. 4 of them are on the board behind me. The 5th one is the California current, which is our local current, but it's just like the Canary current because it's also an eastern boundary current, like the Canary current. The 6th current is on your screen right here. It's called the Antarctic Circumpolar Current, also known as the West Wind Drift, also known as the Penguin Gyre. I will call it the Antarctic Circumpolar Current because while that name is very long, it is very descriptive. Where is it located? Off the coast of Antarctica, obviously. How is it moving? It's moving around the pole. That's what circumpolar means. It means it goes around the South Pole. There you go. So why does it move around the South Pole? Why does it completely encircle the Earth down there in the Southern Hemisphere? Because there's no land masses getting in its way. It can sneak between Antarctica and Australia. It can sneak between Antarctica and South America right there at the red dot there. It's a narrow gap, but it can still get through there. And it can sneak between Antarctica and South Africa. Plenty of space there. There's no roadblocks. So this current never has to change direction, right? So if you look up here, look up here, the Canary current, the North Atlantic current, it crashes into Europe and it has to head south. And that's why we get the Canary current. The North Equatorial current here crashes into the Americas and it has to turn and head to the north. And that's why we get the Gulf Stream current. All of these gyres, when they move across the equator or move through the northern part of the ocean basin, it will end up crashing into some landmass on the edge of that ocean, and it will have to change direction. The Antarctic Circumpolar Current never has to change direction because it never crashes into a landmass. It just sneaks its way through. Not only does it sneak its way through here, but as you see on the slide, the westerlies down there, the surface winds of the Ferrel cell in the southern hemisphere, they end up pushing it. The other way. They end up pushing it all the way across. Push, 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 push. If I had a basketball spinning on my finger and I could push it with one hand, it might go pretty well. But if I had a bunch of hands all pushing on it all the way around, push, 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 that ball could be going very fast, very steady, very consistent. And that's what the westerlies are doing. They're pushing on it every stretch of the way, all the way around. So it is hustling. It is moving swiftly, which is what allows it to move more water than any other current. If every other current was flowing kind of like I said before, like a garden hose, this is your fire hose kind of a current. And while the other currents, as you can see here on the diagram, some of them are red, some of them are blue, some of them are warm, some of them are cold, somewhere in between. The Antarctic Circumpolar Current is freaking cold. It never has to leave the coastal region of Antarctica, known as the Southern Ocean, so it never has to go anywhere where it could warm up. In fact, it just gets it got cold and it just sits there and it just stays cold. So this is just a kind of a recap here. We're just about finishing up. In the North Atlantic subtropical gyre, there are 4 currents that I want you to know: the North Equatorial Current, the Gulf Stream, the North Atlantic Current, and the Canary Current. Those are 4 of the 6 currents I want you to know. I want you to know the names, the directions, the speeds, relative speeds, not actual numbers, just fast, slow, medium. Temperatures, relative temperatures. Are they the warmer ones, the colder ones, or somewhere in between? And the reason I did this, the reason I only drew one gyre is because if you can understand what's happening in the North Atlantic gyre, while the names of the currents will be different, you can also know what's going on in the North Pacific Gyre, or even the South Pacific Gyre, or the South Atlantic, or the Indian gyres, because they all have the same types of currents, the 4 types of currents, and the same patterns exist in all of them. But as far as the names go, it's just these 4 plus the California current and the Antarctic circumpolar that we just talked about. A couple other things to note. Let's zoom in on a couple of these currents just to see some unique aspects. The Gulf Stream, you can see it pretty clearly here along the East Coast. As I said, it's a narrow current. You can see just how narrow it is. It is literally getting squeezed between the East Coast and the hill of water out here due to the subtropical convergence that we talked about before. But you also see here, as it moves northward off the coast of, gosh, I guess that's like Virginia, Maryland, or whatever, it's no longer being so tightly squeezed between the East Coast and the hill of water. And so it kind of has a little bit more freedom of movement. And we see that freedom of movement take place, and it kind of behaves kind of like a flag flapping in the wind. It's no longer being constrained here. And so it kind of flaps around a bit. And sometimes it will flap around so much that the current will kind of loop back and close in on itself. And it gives you, if it loops in and it closes in on itself, it will kind of grab some of this water. In this case, it will grab some water from the north of the current, this cooler water, and it can pull it to the south. And those are called cold core rings or cold core eddies. These little pockets of cold water surrounded by what is otherwise much warmer water. And the other thing can happen too. It can kind of loop the other way as the flaps the other direction. It can kind of close in on itself, and it can grab some of that warmer water from the south and pull it northwards, giving you a little pocket of warm water surrounded by cold water. That's called a warm core ring. And you can see that here. And again, this is something that the fishermen are going to keep track of, because when you get that cooler water up at the surface, it's easier for the deep water to upwell there, bringing nutrients, and the fishing's going to be good. We also see that this Gulf Stream, as I drew it on the board, let me go back here. As I drew it here on the board, it was kind of like an idealistic scenario. Sometimes though, this water comes into the Gulf of Mexico and then it heads back out. That over here, that's called the loop current. Let me go back. Share. There we go. This is called there we go. This is called the loop current. Now, if you recall, when we were talking about hurricanes, specifically Hurricane Katrina, when she comes in across southern Florida and enters the Gulf of Mexico, she hit a pocket of warm water, that made Hurricane Katrina go from a Category 1 to a Category 5 in just a couple days. And she became massive. It was the loop current that happened to be there that week with exceptionally warm water that had just come from the equator. And that's what caused, as we said before, warm surface ocean water is the fuel for a hurricane. And so she got massive. But remember, we also said that when she makes landfall, I'll show you right here off the coast of New Orleans, there was a pocket of cold water there that caused her strength to be diminished at the last minute. Just before making landfall, she drops from a Category 5 to a low 4, high 3 category storm. That was one of these cold core eddies that was sitting there, cold core rings sitting there right off the coast of New Orleans, that, as we mentioned before, probably saved billions of dollars and maybe, dozens, if not more, hundreds of lives because of the storm kind of weakening at the last moment. There you go. You can kind of see what it actually looks like with the temperature of the water. You can kind of detect when the loop current comes into and then flows back out of the Gulf, joining the rest of the Gulf Stream. As we mentioned before, the climate effects of these currents, the Gulf Stream off the East Coast of the United States has a very distinct, noticeable effect. If any of you have been to Florida, it was probably warm and humid while you were there. And it's like that all year round because the Gulf Stream is always right next to it. In fact, when the loop current is there in the Gulf, it's surrounded on both sides by really warm surface ocean water, which warms and humidifies the local climate and weather patterns. One thing I forgot to mention, I want to mention it now, even though it's kind of out of place. The Gulf Stream, because it moves so fast, we end up delivering, it ends up delivering a lot of warm water into the North Atlantic Ocean. And that's for two reasons. One, it moves really fast, so the water is actually not being given a whole lot of time to cool off. And the other thing is, which we've already learned, water has a high heat capacity. Water as a substance is very slow to cool off just because it's water. And so the Gulf Stream delivers a lot of warm water to the North Atlantic Ocean because it gets the water there so quickly, and it doesn't give it much time to cool off. So it allows these North Atlantic current here to also affect the climate in places sometimes like way up here in Iceland or over here in the UK. If you look on this map, right, like the United Kingdom here, so Ireland, Great Britain, Scotland, England, whatever, those places, they're at the same latitude as like northern Canada. I'm not even talking about like Toronto and Quebec. I'm talking like northern, further north than that. Look at the latitude. Look how far from the equator they are. But it has a climate that is nothing like the bitter, brutal, cold winters that you see in Canada. Does it get cold in the UK? Of course it does. Do you get like, is it common to get like 4 to 6 feet of snow during a snowstorm? Hardly ever. I mean, they're known for more rain and fog and not the really, really cold, brutal temperatures, because the heat from the Gulf Stream entering the North Atlantic current keeps the climate there in the UK more mild than it otherwise would be. Those north moving currents that are warm, they end up doing that. The south moving currents, like here, the Canary Current, are cool. And again, the California Current is just like that. So let's think about like practical applications of this. What do we grow in California? We grow grapes because we're known for nice wine. We grow citrus. We grow figs and dates. And we grow a lot of crops like that. They grow the same kind of crops over here in Spain and France, obviously known for wine, and Portugal and Northern Africa, the figs and the dates here, places like Morocco. Their climate is very similar to ours because their coastal current, the Canary Current, is very similar to the California Current, simply put. And that's it for today. Thanks for hanging in there. Hopefully you took some notes. Hopefully you wrote down which questions you have. If you didn't do that, you can flip back and start this thing over, and you can kind of keep track of where the tricky parts were. Please ask me your questions on the discussion board on Canvas, or log into my Zoom virtual office hours. The times for those are posted on Canvas. We'll see you there. But for now, that's it. Thanks. Here we go.